Hi everyone, this is Eukabuka and welcome to my home on YouTube. On this channel, I will be uploading videos related to my ventures in understanding the Linux kernel. Often when I try to understand some source code, I find it very helpful to be able to poke and prod the system. In this video, we will discuss how we can set up a minimalistic ARM64 Linux system that we can prod in the future videos. At the end of this video, we can also take a look at how we can use the QEMU GDB stub to debug the Linux kernel. The machine I am recording on is a Mac OS X. I have SSH'd onto a Linux box, and that is where I will be working in this video. Alright, let's get to it. So the steps that we will be going through are as follows. First, we will try to set up QEMU for ARM64 because in this series of videos that I'm about to make, we will be concentrating on the Linux kernel, on a Linux kernel built for ARM64. So we will try. The reason for choosing QEMU over other virtualization solutions such as VMware or VirtualBox is that it's possible to create a lean, fast, minimalistic user space system very easily and have it boot up with QEMU. And it's also possible to have a very easy kernel debugging setup. So the first step will be for us to set up a QEMU for ARM64 or ARC64. The second step will be to create an initramfs CPIO file using buildroot. And the third step will be to compile the Linux kernel for ARM64. After that, we will boot up the Linux kernel using QEMU, and we will show how it is possible to debug it using a GDB stub. So let's start off with trying to build QEMU. So on my machine here, I've already downloaded the source for QEMU, and that can be obtained from wiki.qemu.org/download. And the version I have downloaded here is QEMU 2.8.0 RC1. So once you've downloaded the tarball, you can extract it and cd into the directory, and the build commands are rather easy. It's /configure and a make. In this case, however, I have already built QEMU, and as a result, I won't be building it again. Once QEMU is configured and built, you can see the ARM64 binary inside here. You can see QEMU system ARC64 is the binary that we will use. Note that you may be able to use QEMU system ARC64 from your package manager that you get, RPM or apt-get, whichever OS you are on. But I think it would probably be advisable to go for the latest release that QEMU offers. On this page, you can see that the latest QEMU release is 2.8.0 RC1. So now that QEMU is built, the next thing we do is build an initramfs CPIO file. And how we go about doing that is by using buildroot. You can obtain buildroot from this website here. Buildroot. The package that I downloaded for the demonstration here is the second link on the page, that is buildroot 2016-081 tar.bz2. Now you can see that I have buildroot over here, So you download the tarball, extract it, and visit the files inside. You can see that this is the layout of the files inside. And the next thing you need to do is make menu config. Yes, my display is a bit too small, so I need to realign that just a bit. And make menu config again, and I can see that this is the menu that I'm presented with. There are a few options that I need to set inside this. As I have already used build root once on this machine, I will just walk you through the settings that I have set for this particular configuration. Inside target options and target architecture, I have set the architecture as AArch64 Little Endian. That is the choice you should make. Inside build options, there are no options that need to be configured. Under toolchain, you need to choose the toolchain type and choose the external toolchain option. By default, it's the build root toolchain option. And when you choose that, this option here should change to Linaro ARM64 a year and a version. So this is the one option that you need to set in the submenu. System configuration, there are two options that you need to set. One is that you need to set a root login password over here. In this case, this is just a test VM, so I've just set it to something silly. And the next one is to set your login prompt. So you need to select the option here, run a get TTY login prompt after boot. And once you select that, you need to change the TTY port to TTY AMA 0. This is very important. If you do not set this, your VM may not boot. So you need to set the TTY port to TTY AMA 0. There are no other changes that need to be made in this submenu. So we can go back. We don't need to set anything inside the kernel. We will not be using build root to build the kernel. We build the kernel separately. Target packages. We choose the options show packages that are provided by BusyBox. Additionally, under debugging, I also select strace because I like having strace when it comes to debugging. Under editors, you can choose your favorite editor, and in this submenu, that's about it. After that, you need to choose the file system image that you want build root to produce. So when you go inside the file system images submenu, you can see that you have various options. You have AXFS, CLoop, CPIO, and so on. In this case, we choose this option. We need the output in the form of a CPIO root file system image. So we select that option and then we hit back again. There are no options to be set under bootloaders, host utilities, or legacy config options. So that's about it. At this point, we exit the menu and we can see the message being printed out: end of configuration, execute make to start the build, or try make help. So so now that we have finished configuring the build root environment, we can simply type make and the root file system will be built. Something that is interesting is that the configuration file that we just created can be seen in the .config file. So here you can see the various options that have been set inside this configuration file. So you can create a backup of this config file and then use it later on if you wish to. So it's pretty handy. So as I've executed make once earlier. I won't do it again. However, after you execute make and once the build succeeds, your output file will be inside output images as rootfs.cpio. That will be your output file, images rootfs.cpio. And doing a file, you can see that it's an ASCII CPIO archive. All right, let's go back to our summary once again. So now that we have set up QEMU for ARM64 or ARC64, and that we have created a CPIO rootfs file system, the next and the final step is to compile the Linux kernel for ARM64. Now we can obtain the Linux kernel from this website here, and the version that I decided to download for the purposes of this demonstration is the stable 4.8.11. You can get the tarball from this link here. I have already downloaded it on this machine and won't be doing it again, but this is where you can obtain the latest stable source code tarball from. So you can go to repos, Linux kernels. In this case, this is where I've downloaded it, and this is the tarball here, which you can extract. And once you go inside, this is what you see. These are the files. Now, the architecture that we are going to build the Linux kernel for is ARM64. And when building the Linux kernel, you specify a configuration file which decides how the kernel is built. Now, for each architecture, there is a default configuration file, and that can be found inside architecture name, which in this case is ARM64, configs, and we see a def config file. Now a def config file stands for default config. The idea is to tell the kernel to build using this def config and a few other changes which we will make. But for the most part, the configuration files are going to be exactly the same as def config. So let's just go back to our earlier directory. And the first command that we will be executing is arc is equal to ARM64 cross compile is equal to arc64 linux-gnu and make def config. This is the command that we will execute first. Now, I must say that before cross-compiling a kernel for ARM64, you need to install a cross-compiler toolchain for your OS. If you are working on an Ubuntu machine, then it is very easy. You can get an ARM64 cross-compiler toolchain using apt-get, using the apt-get package manager. Once you have the ARM64 or ARC64 toolchain installed, you can execute this command to get the default config on your current working directory. So once you execute this, you can see that the default configuration is based on def config, and that configuration file is written to the .config file. So if you open the .config file, you can see that the def config file has been copied over to the current directory as .config. When you build the kernel, the .config file is what will be used. So if there are any options that you want to set manually, it needs to be set in this file. So let's proceed to set the two config values that we want to. The first one is CMD line. Not this one, but the next one. Yes, and in this case you want to set it to console equals tty ama 0. That's what you wish to set it to. The next option you want to set is initramfs. And the option name is config initramfs underscore source. And you want this variable here to point to the rootfs.cpio file generated by buildroot in the second step. So let's just find the path to that directory. You have repos, buildroot, output, and images. Let's just go to the previous directory, .config, and there we go. So now config initramfs points to the CPIO file that we just created using buildroot. And those are the two options. Let's also set config debug info in case it's not set, but it seems to be already set. Debug info. Yes, so this option is already set. All right, seems good. And once this is done, the command that you want to execute is arc is equal to arm64 cross compile is equal to similar to the earlier command, except that you can do a make-j8, a j8 depending on how many processors you have on your machine. So if you have a multi-core system which is pretty fast, then you can try -j8 based on how many cores you have. And I'm not going to build it right now because I already have it built before making this video. So yes, once the kernel is built, we will have the following files. The first one is the VM Linux file, and the VM Linux file is an ELF 64-bit ARM64 file that is created as the kernel is compiled. As for the core kernel, you can find it inside arc ARM64 boot and image. This is the kernel that we just created. Alright, so now that we have completed all the steps, that is compiling QEMU, compiling buildroot, and making a rootfs image and compiling the kernel, let's use QEMU to bring the system up. I have a file in my home directory as start.sh that I use to start up the kernel. And this is how the command looks. You can see that the first one is just the path to QEMU system ARC64. And then these are options that specify the kind of the processor that QEMU needs to emulate. The -m flag specifies the RAM size. The -kernel flag specifies the path to the kernel that we just built, as the script resides in the root of the Linux kernel source. The path that I'm passing is a relative one, and we append the console is equal to tty ama 0 argument as we bring up the kernel. The $1 and the $2 are, I'll get to why I use the $1 and $2. It's there mostly for convenience, and I'll get to that soon. But for now, let's try bringing up the kernel that we just built by executing the script. Okay, try start.sh. All right, and that's it. The machine is up and running. So this is what I mean by a minimalistic user space system. For purposes of demonstration or for purposes of learning more about the kernel itself, it's super useful to have something that boots up really fast, something that you can compile. If you make a change to the kernel, say adding a few print case or making some change, and then you want to build it again, you want to bring it up again using QEMU really fast. You want that cycle to be fast, and that is why I prefer the setup a lot. Let's try logging in as root, and the password that we set up in build root, and we have a prompt. So if you go back, you can see the file system, you can see the commands that are there, you can see that there is strace, you can see that's pretty much it. So if you want to stop running the VM, the shortcut is Control A and C followed by a quit. That's Control A, C, and quit. I believe that Control A, X also does the same thing, but I'm just more used to using Control A, C, and quit. Okay, so now that we have gone through setting up of QEMU, creating an initramfs, and compiling the Linux kernel, we get to the last stage, which is debugging the Linux kernel. In the next video, we will look at how we can debug the Linux kernel using the setup that we have currently. That's it for this video. If you like this video, hit like, and if you wish to be notified of future videos, hit subscribe.